Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video illustrates the use of OpenCV to calibrate a camera. Since OpenCV, the most popular open source solution for computer vision processing, has solutions for the detection of markers, in the interest of expediency, it is more pragmatic to leverage OpenCV for further exercises with the Tello EDU drone. These exercises are currently under preparation, but first things first. The camera in the Tello EDU must be calibrated to derive reasonably accurate distance measurements. This tutorial examines the basic steps for the calibration of a camera using OpenCV utilities and example programs. Once the steps are streamlined, the process can be applied to any camera whose feed can be captured by OpenCV. The OpenCV repository has two examples for camera calibration. One in Python that is almost 4 years old, and the other in C++ that is nearly a year old. There is fascinating mathematics behind the key computational algorithm for the calibration based on a paper by Microsoft Research that is worthy of reading, but well beyond the scope of this tutorial. References to the links to two key publications are listed in the description section of the video. While it is possible to use different patterns to calibrate the camera, the basic requirement is the presence of fiduciary markers on the object. The checkerboard fulfills this requirement with its intrinsic corners. The checkerboard pattern, that is the number of internal rows and columns, is a user choice. For our calibration exercise, we have several different checkerboards with differing number of rows and columns. The checkerboard is viewed through the camera at different positions and angles that are captured and saved as files for use during calibration. Since the detection of corners in an image is a prerequisite for that image to be used during the calibration calculations, it is best not to save an image whose corners cannot be detected. Finally, after a reasonable set of images has been collected, the camera parameters can be estimated using the OpenCV utility routines. The key requirements for the pattern are dimensions known precisely, image captured from different viewpoints. Although circular patterns can be used, the checkerboard is the most common pattern for calibration exercises. The sharp gradients at the corners of the squares in a checkerboard facilitate the detection in the two axial directions. If one corner of the checkerboard is referenced as the origin of the global 3D coordinate system, then the coordinate points for all the detected corners can be derived since the width of the squares is known. For camera calibration purposes only, and this is a very important clarification, this particular checkerboard is stated as having 8 inner corners in the column-wise manner and 5 inner corners in the row-wise manner. For our testing purposes, we specify this pattern as 8 by 5. Also note that the square size is the width of a single square in the units that will be used to represent the focal length of the camera. For our use, we prefer to use millimeters for the camera focal length and therefore specify the width of the square, also referred to as square size in the code, in millimeters. If we assume that the lower left corner of the square at reference 1, 1 in the slide is the world coordinate origin, that is 0, 0, 0, then since we know the width of the squares, we also know the coordinates of the other corners in 3D space. From the captured image at a known resolution, we can also obtain the corners in terms of pixels in the image frame. Once we have captured a reasonable number of images, it is basic matrix algebra to correlate the 3D coordinates with pixel coordinates to obtain the focal length of the camera. This is the primary essence of the algorithm published by Microsoft Research. The inference is provided in the description to the video. There are 2 ways to capture the images of the checkerboard. One can keep the camera stationary and orient the checkerboard at different angles for the shots. Or one can keep the checkerboard stationary and move the camera to different viewpoints for the shots. The calculations will not be different for either mode of operation. It would be desirable to have a large number of images for refined accuracy in the calculations. For the very limited purposes of this introductory tutorial, I opted for 30+ images per checkerboard. I used several different checkerboard geometries to acquire the images. Naturally, each checkerboard pattern was constrained to one set of calculations. It is good practice to check for corners in a captured image before saving it for further processing. If no corners are detected in an image, in other words, the connection between the detected corners is not overlaid in the display window of the captured image, then that image will not be useful in calibration calculations. Therefore, it should not be saved for further use. Let us look at how we want to capture the checkerboard pattern. So we're using the 8 by 5 pattern as shown on the slide, and we're going to go ahead in the first instance, keep the camera constant, but move the pattern around on the floor. We were going to collect at least 30 images in this orientation before we move on to another pattern. In the second mode, we will keep the pattern, the checkerboard pattern, stationary and move the camera around. So this will give us 2 distinct sets of images, but both sets of images yield identical camera parameters. So there is no difference in calculation whether you move the board or you move the camera. Do whichever one suits you best in terms of your own setup, and then don't forget that you should not save any image that does not have the corners drawn in the displayed window. If the system cannot detect the corners, then there are no points to be fed to the calibration program, and that image will not be useful. The simplest way to record an image is to use one of the commonly available apps on your desktop. In the case of Ubuntu, we have something called Cheese that we can use to capture either a video or a photo. In this case, it's mainly photos, and we go ahead and click it. Cheese is easily installed, and just make sure that you're using the latest version, obviously. And it has a list of credits about who supplied where. And you can go ahead and move the board and then take individual pictures and save them to a designated folder that you will then feed to your calibration program. It may be easier to use your own custom script to capture the images. So what I've written here is a sample Python script to capture the images through the same webcam. So there is a function here that requires these parameters, and I'll just scroll down to show you what those parameters are. So basically, it's the number of horizontal or column inner squares, the number of vertical or rows of squares, inner squares, and the square width. I supply this as a list to the calling program, and then we run it. So when we run it for the first time, it'll come up with a very simple warning message regarding video captures that you can safely ignore. And then it gives us this prompt here that you can press the space bar to save the image. The image is displayed by OpenCV, and it has identified the inner corners of the image and represented them in alternating colors. If you are satisfied with the number of corners that have been detected, which should be the same as the original specification, you can hit the space bar and save the image. Once you've done that, there is a confirmation message that will be displayed, and at the end of that, then you proceed to capturing the next image. So we have a very simple loop. We hit the space bar if we are satisfied with the detected corners. Then the system confirms that the image was saved, and that is why we have another key press there, and we could literally press any key. And then the cycle will resume only if you don't press the letter Q. If you press the letter Q, that means you've satisfied with all the images that have been collected, and it's time to stop the program. Once the letter Q has been accepted by the program, a termination message is displayed on the screen. The OpenCV package has sample code for the calibration of any camera. There is a slightly older version of the example written in Python. Then there is a more recent version written in C++. Both programs perform the same operations with respect to the initial calculations for the calibration. The C++ program continues further processing by estimating a new camera matrix. It also renders an undistorted image for reference purposes. The calculation assembles a list of 3D points based on the input data pattern, that is, number of columns and the number of rows, as well as the square size. Whatever units are used for the square size, the results will be estimated in the same set of units. The C++ program is a little more comprehensive than the Python. The Python was strictly focused on reading the images and detecting the corners and then doing the calculations. The C++ program not only does it for chessboards, but also does it for other kinds of geometry in what is known as April tag or even circles. So it's a little more involved, but obviously since it's more recent, it is a little better to use if you have the bandwidth to go through some of the essential requirements. So I will not try to educate you on the C++ program here, but if you do have any questions, please drop in some comments and I'll get back to you and help you make better use of this program. As you can see from this screen here, there are several different options for the images. And obviously, in our case, we are limiting ourselves to the chessboard corner, and we're going to go ahead and calibrate the camera based on the chessboard corner images that we have selected. So essentially, the first part is almost similar to the Python program. In other words, it'll open up the correct folder and then it'll read the files. But the advantage of the C++ program is that it uses a settings file to figure out where the files are kept, the images, and it reads the images from that information. So I'll be demonstrating it from a command line environment rather than running it in this kdevelop IDE environment. And then the other advantage of this is it can write the files to a folder. As you can see that it at the end of the program when it runs, it can save it if you choose to do so. It'll be very helpful to read it back in some other program where you're going to use the camera parameters. There are two key files that we have to pay attention to when we are running the C++ version of this calibration program. One is called default.xml, where the configuration information is saved, and then another one called images.xml that is referenced in default.xml that contains a list of images that have to be fed to the program. Remember, we're using chessboard option here, right? So let's take a look first at the images.xml file. And as you can see, it's nothing but a list of all the images with the fully qualified name to avoid any ambiguity. So I'm using a 6x4 inner corner with 47mm wide squares, and the files are listed there in that order there. So we have quite a few files, enough for the calibration, and I'll exit from here. Okay. Now let's take a look at the default.xml. And in here, the key parameters are the board size and width, and then the square size. Everything else remains the same. As you can see, we're telling it to use the images.xml file that is in the current folder, and we're going to be using the chessboard pattern for our calibration. For now, that's more than enough for us. So let's go ahead and exit from here and run the program. So the executable is maintained under build, since that's where the kdevelop environment placed it. So just want to show you by going in there and where it is. And as you can see, the file is called camera calibration. And we're going to be running this with the default parameters. So let's run the program. And we're going to be using basic default settings for the images file and the settings files. So the images files is images.xml, that's defined with the list of all the images that are going to be processed, and default.xml, among other things, references this file and also provides information on the chessboard pattern geometry. So we hit enter and run. the output is written to a file called camera out underscore camera underscore data.xml. So let's go ahead and look at it. Out camera. And as you can see, it does a lot more than the Python program. It lists all the coordinate points for reference purposes. And right at the top, it has the camera information in JSON format so that you can then import it elsewhere if you choose to, right? So. And hopefully this is going to help you better than the Python program. So it's really your call on whether you should be using the Python program or the C++ program. I would recommend that you use the C++ program because it has a lot more bells and whistles for you to customize and to fine-tune. Naturally, you could do the same thing in the Python program, but with a little more elbow grease. The other thing to note in here is that you don't have to use the kdevelop IDE. You can use any other C++ IDE that you have, or even just use the simple CMake from the command line if you're not making too many changes to the code. Here is the summary of the results using the Python script and the C++ program. I've used the same checkerboard patterns in both cases for consistency. And as you can see, in the case of the Python program, the range for the focal length in X and Y is pretty consistent. The same thing is true for the C++ program. It's consistent within that set. But there is a slight difference in the numbers when we average them out. In other words, we would like to perform some more tests before arriving at a set of numbers that we could use more authoritatively. Fortunately, for the center in X and Y, the numbers are pretty close and we don't have to worry about it. The distortion coefficients naturally are slight all over the map, and again, further tests are needed. So I hope that you understand that it's not enough to be satisfied in testing with just a few test cases. For more rigorous testing, it would be preferable to perform some more tests so that we can quite considerably be sure that the values that we're using for pose estimation and distance calculations down the road are pretty much within the ballpark. This interim video tutorial demonstrated a simple process to calibrate cameras using the OpenCV libraries. Several different checkerboard patterns were prepared. Approximately 30 or more images from each pattern were captured as sets per pattern. Each set was processed by two sample programs in the OpenCV module, one in Python and the other in C++ to calibrate the camera. The results for the Python processing were congruent. So were the results for the C++ calibration program. But there was a minor difference in the focal lengths for the two different sample codes. Perhaps there will be an opportunity in the near future to drill down further to examine whether the differences were due to termination or refinement criteria. Time permitting, it would be desirable to conduct more tests on different checkerboard geometries before applying the processing pipeline to the Tello EDU camera. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance from OpenCV for image capture and the camera calibration programs, and from free open source software for the two integrated development environments IDE, from PyCharm for Python and Kdevelop for C++. Also, the backbone for the preparation of this video is from Inkscape, OBS Studio, Kdenlive, and LibreOffice, not forgetting Ubuntu. Family, teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you for the assistance. There are three options for the installation of OpenCV. If you are using PyCharm IDE for your Python development, then it is best to leverage the PyCharm feature for installation of OpenCV. The second method is to use sudo apt as a general package across the board. The third method is to use pip, especially in a virtual environment, which is highly recommended for any kind of Python development. In this segment, let us review the steps to install OpenCV using the PyCharm IDE. Once we have launched PyCharm IDE, we can click on Projects to get a list of all the available projects. You may at this stage want to create a new project for this demonstration, or I'll just go and use the first one available called Utilities. A new window is launched for the project called Utilities. On the top menu bar, the main menu, there is a hamburger toolbar that you can click and select Settings from the drop-down list. In the Settings window, drill down under Project Utilities and select Python Interpreter, or select Python Interpreter in the right pane. The list of packages installed will appear in alphabetical order. You want to select the plus sign above the list to specify OpenCV. So we go ahead and click on the plus sign here. A new window will pop up listing all the available packages that can be installed. We'll go ahead and insert OpenCV, so OpenCV, and search for all the packages that are related to OpenCV. We are looking specifically for OpenCV-Python. So scroll down, up or up, as the case may be, and locate OpenCV-Python. On the right-hand side, in the middle pane, under Description, the ownership of the package or the source for the package will be displayed. The link here is for GitHub OpenCV. So this is indeed the genuine package, and we can go ahead and select that we want to install that package. Before we do that, we can choose a specific version if we want by clicking on the checkbox and scrolling down the list of version numbers. In our case, we don't want to do that because we want just the latest version available, and there are no options to be installed. So go ahead and click on the button Install and let the installation proceed. Once the installation is complete, a status message indicating the successful installation is listed at the bottom of the pane. Package OpenCV-Python installed successfully. You may want to just go ahead and scroll down the list if you want to and take a look, and sure enough, we see Python OpenCV now installed in here, and that is the latest version. We click on OK to dismiss this, and that concludes the installation of the OpenCV package. In this segment, we will demonstrate the installation of OpenCV from pre-built binaries. So before we do that, let us go ahead and ensure that our system is up to date. Sudo apt update. And hopefully it should come back and tell us that no updates are required. And now we can go ahead and type the command to install Python 3-OpenCV. So it's Python 3. As you know, Python 2 has been deprecated and is generally not available except in prior installations. But nevertheless, we still have to use the suffix 3 to indicate the version of Python. So we type in sudo apt install Python 3-OpenCV and hit the enter key. And since we've already installed it, it tells us there's no further installation required. In your case, maybe it'll scroll through a whole bunch of packages to be, the dependencies to be installed. Notice here that the version is 4.5.1. Generally, this is not the latest version of OpenCV that is available from the official site. But for our purposes, this version is good enough. So I go ahead and test the installation, invoke the Python interpreter, and then import the OpenCV library. And sure enough, it's recognized the thing and it's processing it. And now we can go ahead and type the version number out. So it's echoing the correct version number for us. Let's exit the interpreter. So once again, if you do need a later version that is not in the repository, your only recourse will be to build it from the source at the official GitHub repository for OpenCV. This is perfectly fine for those who are interested in doing extended development, but for our purposes, for the Tello EDU demonstration, 4.5.1 is adequate. In this segment, we will demonstrate the use of the Python virtual environment to install OpenCV. To create a virtual environment, you can type in the command python 3-m venv and then the name of the virtual environment that we would like to use. So in this case, it's testcv. And this will create a virtual environment under the label testcv. Since I've already done this, I'm not going to go ahead and execute the command, but just change my directory to that folder. So you can see that folder exists. And now we need to activate the virtual environment. So the way to do that is to type in command source, and then we are already in that directory, so we have bin activate, and this will run that. And notice now that the name of the virtual environment is prefixed on the command line prompt. So we have our virtual environment for Python, and now we're going to go ahead and install OpenCV. So once again, I'll use Python 3 so that we don't get confused by which version is active, and OpenCV-Python. Since I have already installed Python, OpenCV in this machine, it is going to come back and report that it's already present, as you can see in here. So a quick confirmation would be appropriate for what version is being used. So we go ahead and type import cv2, and then we type in cv2 underbar version underbar. And you can see that the version number here is 4.6. When we installed from the command line sudo apt method, it was 4.5.1. So you can immediately realize that there are various versions of OpenCV from the different repositories, and you've got to be quite careful about which one you're using. Of course, the latest is always available if you build from source.